Continuing with chapter 2, here we're going to take a look at the chemical composition of the body. And so we're going to do first a quick review of general chemistry, and then we're going to take a look at the organic molecules of life in the second half. So we're going to start here out with a basic review of chemistry. And so all matter is composed of atoms. An atom is defined as the smallest unit of matter that can no longer be divided. Now we already know that these atoms, they are composed of subatomic particles, and the good news is that you really don't need much detail on this. So a very basic kind of review of chemistry here will do for us. And so we're going to take a look at the atoms and what they're composed of. So in the nucleus of an atom, you find protons and neutrons, and then zooming around, surrounding this, nucleus, you find electrons. Neutrons do not carry a charge, but protons carry a charge and electrons do too. So you have the charge listed right here. Protons, that would be positive charge, and electrons, that would be a negative charge. The charges need to balance each other out, otherwise your atom will be an ion and will carry a charge. But let's take a look at the simplest of all atoms. Here first we have a hydrogen. That's just composed of one proton in the nucleus, and that has to be balanced out by one electron surrounding it. Now I realize that this is a very old-fashioned model here of how these electrons zooming around the nucleus, but it will be perfectly fine for the purpose of this course. So just picture these shells, what they used to be called. It's a very old model, but it's great for what we need, and no need to make it more complex than what it needs to be. So here we have a little bit bigger atom, carbon. And there you can see carbon is number 6 on the periodic chart of the elements, and so therefore it carries 6 protons. These 6 protons, they carry 6 positive charges that have to be balanced by 6 electrons, 6 negative charges. And then to keep the protons stable in the nucleus, we're going to add 6 neutrons that don't carry a charge. The atomic mass is always the sum of the protons and the neutrons, and each proton and neutron gets a mass assignment of 1. So carbon, well, we're going to have to add 6 protons and 6 neutrons together, so that would be a mass assignment of 12. And so therefore 1 mole of carbon would weigh 12 grams. Now you might ask, hey, how about the electrons? Well, it's negligible in terms of mass, and so we're just not going to count them. Sorry. Going to neglect those little guys. Okay, as I said, we're going to deal with just a very simple model in terms of the electrons and outer shells and all of that, because all we need for the purpose of this course is how bonding occurs and how these outer shell electrons participate in different kind of bondings. So shells, and I realize it is an old model, but it's perfectly fine for us. These orbits or shells, they surround the nucleus. And here are the rules. The first shell can hold a maximum of 2 electrons. The second and third shells each can hold a maximum of 8 electrons. And only these valence electrons, these outer shell electrons, can participate in bonding. So valence electrons are the outer shell electrons. An isotope, here as a sidetrack, that is an atom that has the same, so it's still the same element. So let's say we're dealing with carbon that is not carbon 12, but let's say carbon 14, which is an important isotope. Now, how does carbon, which has six protons, to make it carbon, it has to have six protons, but how is it having an atomic mass of 14? And that comes by varying the number of neutrons. So that means the atomic mass is different from the non-isotope version of the atom, of that element, and it has either more or fewer neutrons. So the neutrons make the difference there. So carbon 14 has 8 neutrons plus the 6 protons, of course. Okay, let's take a look at chemical bonds, molecules, and ionic compounds. So a chemical bond is when two or more atoms sort of start interacting with one another. And it's always about the interaction of these valence electrons. So it's always the outer shell electrons. And the number of bonds is determined by the number of electrons needed to complete an outermost shell. Picture that every every atom is happiest when it has a completed outer shell. And so there are two ways to do that. You can either see if you can find extra electrons to fill up your outer shell, or sort of steal them from another atom. Or if you have only one and you don't really need it, you can just give it up, just kick it out, and then you also have a complete outer shell. So there's always this desire of having completed outer shells. And so we're going to take a look at covalent bonds and ionic bonds and how they complete or satisfy that desire of having outer shells that are full. So let's first take a look at covalent bonds. In this case, we share pairs of electrons. Basically, two atoms, they make a deal and say, hey, we're going to get in close proximity and we're going to share a pair of electrons. And here it looks like this. So there's this pair of electrons. And here in this example, hydrogen, it feels now to this hydrogen atom that, oh yeah, great, I have a complete outer shell because the first shell holds 2 electrons. And this hydrogen atom is happy too because the outer shell is full. So everybody's happy. It's a stable situation. It's a very strong bond. It's hard to break. It's like more like a permanent thing. It takes a lot of heat or pressure to break a bond like that. Now, so these are the examples given here, hydrogen and oxygen. Okay, so here another version of a covalent bond here shown as the polar covalent bond. So this one here is completely even. You see there's both partners have equal strength and the sharing of the pair of electrons is completely fair. The polar covalent bond, on the other hand, it becomes a not so fair situation because on the one hand, the two atoms make a deal. On the other hand, one is stronger and says, oh, you know what, I'm just going to pull the pair of electrons a little closer to myself because I'm stronger and I'm better. So anyway, the example here is given for water, H2O. So we have one oxygen, 2 hydrogens. You can tell how the oxygen is much bigger than the hydrogen. And so oxygen has 6 valence electrons, and so it wants to make 2 deals with 2 hydrogen atoms, and both of them are willing to share the one and only electron that they have in exchange for the opportunity to have a full outer shell. But what ends up happening is that oxygen is pretty greedy and it's pulling the pair of electrons between oxygen and hydrogen. So there's 2 pairs. I'm going to put them here in a red line. It's pulling it closer to itself, which creates, of course, electrons carry a negative charge. It carries this polarity. And, all of a sudden have this negative pole. And then here, the electrons are closer to oxygen, so the hydrogen can't really hold on. So it carries a little bit of a positivity on this end right here. So we have polarity. It's not a charge, but it's a polarity. We have a negative pole on the oxygen end and a positive pole on the hydrogen end. And that polarity has consequences. Actually makes life on Earth possible, and that's not an understatement because it creates the high melting and boiling temperature of water molecules. They're attracted to one another because of their polarity, and it creates a bunch of the other properties of water that we will be talking about in another slide. Okay, now let's move on here to the ionic bond. In the ionic bond, you have basically the situation that an atom is desperate. One is desperate to get one more electron, and the other one is desperate to get rid of one electron. Take a look at this sodium atom right here. Sodium is number 11. It has 11 protons. So we put 2 on the first shell, 8 on the second shell. We have 10 taken care of. Now we have to open a whole new shell for one guy, for this guy. And this guy is sitting up and lonely in a whole shell, and sodium says, man, I'd rather get rid of this thing. So it's finding a partner that's just as desperate to get an electron, and that would be a chlorine atom. Chlorine is number 17. So we have 2 electrons on the first shell, 8 on the second shell, so that's 10 total. And then we have another 7 that are riding on the third shell. So full outer shell will be 8, so we have a perfect pair right here. So basically they do to make a deal and they transfer, this electron goes over here and it's now sitting, filling this empty spot. Now everyone is happy. you have full outer shell on this chloride ion, and then you have this full outer shell here on the sodium ion. Now we call it an ion because now these atoms carry a charge, and so now they're called ions. The sodium ion carries a positive charge because it has lost a negative charge, has given up 1, so that's an Na plus. And the chloride ion now carries an extra negative charge, so it's a Cl minus, and these are both ions. Because they carry a charge, this is truly a charge, because of that charge they're attracted to one another, and that's why sodium chloride table salt is a pretty stable kind of substance. There's this attraction of sodium on chloride sort of keeps it together. Okay, here the example with the ionic bond. They form really nice hydration shells. So in other words, picture dissolving salt in water. It's pretty easy to do. It dissolves nicely in water. Why? Because the sodium ions and the chloride ions, they carry a charge. And then water molecules, the oxygen end that's slightly negative, that has this polarity, negative polarity. The oxygen end of each water molecule is kind of attracted to that positive sodium ion. And here on the chloride side is the opposite. The hydrogen end, the slight positivity of the hydrogen end of each water molecule is attracted to the chloride ion, the negativity, so the Cl minus there. So now you can picture that this sodium chloride table salt would dissolve easily in water. So the sodium and chloride dissociate and they dissolve easily in water. So they have these hydration spheres that you can see right here. And when you write the chemical formula, it will be NaCl that dissociates the sodium ions and chloride ions and dissolves easily in water because water has polarity and sodium and chloride both carry a charge. Okay, continued here on the ionic bond. So here we have two important terms here, and those two important terms are hydrophilic and hydrophobic. So when you have ions or you have polarity, polar covalent bonds, then what happens is that they all like to be attracted to water. So we have substances, I'm sure you're aware, glucose, amino acids, they're all water soluble because they either have polarity or they are ionic in nature. And so they have these hydration spheres, this forms around the atoms or the molecules. And that makes them water soluble, and we call that hydrophilic. That's an important term that you need to know, hydrophilic. Anything that likes to dissolve in water that has either polarity or carries a charge. These are all hydrophilic substances or molecules. Anything that does not have a charge and has no polarity cannot form these hydration spheres, and so therefore does not like to dissolve in water, and that would be all of the hydrophobic molecules. Hydrophobic, that means it's fears water. Hydro is water, phobia is a fear. It's fearing the water. It doesn't like to mix with it. So any of the oils, fats, anything that has no polarity and no charge will not be able to dissolve in water, and we call it hydrophobic. Okay, now the last bond that we're going to be talking about is the hydrogen bond. And the hydrogen bond, that is a very weak but important bond. So in a hydrogen bond, what happens is that you have this weak attractive force. Here the example is given, the attraction of water molecules to one another. And basically what it is that polar molecules that have polarity, they're orienting themselves so that the negative part of the molecule is attracted to the positive pole part of another molecule. So here we have just water molecules in a bucket, and that's the reason why water is still liquid at room temperature, because these hydrogen bonds are holding the water molecules together and they will not go into the gas phase so easily. Now if you heat up the water, then these hydrogen bonds eventually will break and the water will go into water vapor and will be going to a gas phase. So as far as water is concerned, this is a very important property. We need to have this polarity. So we have these hydrogen bonds, these dotted lines. That's what we call the hydrogen bond. They're relatively weak. They're relatively easy broken, but they're super important because they determine the properties of a molecule. And so here, the properties of water are listed right here, and this is just some of them. Water has surface tension, it has capillary action, it has adhesion, it has a high melting and boiling temperature. So all of these are very important properties that actually make life on Earth possible. Moving on to acids, bases, and the pH scale. And so what we have here is first the definition. An acid is a proton donor. It's a substance that puts these hydrogen ions, these H pluses, into solution. The more hydrogens are released, the stronger the acid. A base is defined as a substance that removes these hydrogen ions from solution, meaning that the concentration of hydrogen ion is very, very low then. These things are called proton acceptors, while the acids are proton donors. It's all about protons. Now remember from the beginning, we said that a proton is a subatomic particle. Well, think about it. A hydrogen atom is just composed of one proton and one electron. A hydrogen ion has lost the one and only electron that it has, or that it had, and therefore the only thing that's left is in the nucleus is a proton. So a hydrogen ion is equivalent to a proton. That's all that's left after a hydrogen atom lost its only electron. Okay, so now let's talk about something that's actually very important for physiology, and that would be some acids and bases in the pH scale. You do need to understand that. Some common acids and bases are listed here. I can tell you off the bat, right from the get-go, that the most important ones for this course that you will hear about is hydrochloric acid and carbonic acid. By far, these two are the most important ones. The other ones, you will hardly hear about them at all. So keep it on important stuff. Now, let me tell you about the definition of pH. P is the abbreviation for potentium, which means basically a logarithm, and H is the hydrogen ion. So the pH is the logarithm of the hydrogen ion concentration, and basically it's the negative logarithm. So let me show you how this comes about. So you're expressing the logarithm of 1 over the hydrogen ion concentration. These funny brackets there, that's the hydrogen ion concentration. So let's take a look at this. If I have a hydrogen ion concentration, let's say of 1 in 100 molecules in my beaker as a hydrogen ion. So if I have 1 over 100, that's the same as saying 10 to the minus 2. Okay, so that's the same thing. Or if I have here 1 over 100, so 100, the logarithm of that is minus 2, because the logarithm is the exponent basically of this expression right here. And here we have 1, so we have a negative exponent because the hydrogen ion concentration is 1 over 1/100th. So now the negative exponent right here, the pH inverses that, and so the pH is 2. So if you have this situation and the pH is equal to 2, it's a negative logarithm, so that the exponent, the negative exponent made positive by doing the negative logarithm. Okay, I don't know if you can follow, but anyway, so let's, for those of you who hate math, just tune out for a little bit. I'm just going to explain how the pH scale comes about, and then I'll tell you what's really important. So here, let me give you another example. What if only 1 in 100,000 is a hydrogen ion? Then obviously we don't have as high of a concentration. So now we have the examples 1 in 100,000, and that expressed as an exponent would be 10 to the minus 5, correct? So we have a much smaller concentration, and now the pH is the negative exponent. Negative of -5 is plus 5, so the pH is 5. Oops, I didn't finish this here. pH equal 5 in this case. Okay, so this should tell you, for those of you who like the math, it gives you the explanation of why it is that the acid gets stronger as the numbers, the pH numbers, get smaller. Okay, so for those of you who don't care about the math too much, here's my deal for you. All you need to know is that the pH scale is a scale that goes from 0 to 14. That's the pH scale. You need to know that the point of neutrality is pH 7. You need to know that anything smaller in the pH numbers, as it gets smaller, it becomes increasingly acidic. So the strongest acid would be having a pH of 0. That's pure acid, nothing but acid. And as the numbers get larger, as the pH numbers get larger, we get increasingly basic. So we are having very, very few hydrogen ions. In other words, the concentration of hydrogen ions is 10 to the negative 14, and that would be equivalent to a pH of 14, which is a very strong base. Okay, so that's my deal for you. If you like the math, you can take a look at the negative logarithms. Pay attention mostly to the hydrogen ion concentration, and definitely pay attention to the fact that this scale is a log scale. That means we're going in steps of tenfold. Okay, so in other words, a solution, let me go back to this example right here. So a solution that has a pH of 2 has 1,000 times more hydrogen ions than a pH 5 solution. Okay, the difference here between pH 2 and pH 5 is 3 orders of magnitude. So here was 100th and here is 100,000, so it's 1,000-fold difference in the hydrogen ion concentration. So every pH number is a 10-fold difference. You have a 3 pH number difference, that means it's the one with 3 zeros. That's 1,000-fold difference. Okay, so that's something important to know. So right here, as far as physiology is concerned, well, hydrochloric acid is in your stomach, and then we have a very, very important buffer system that you will hear many more times from me throughout this course, and that is water plus CO2, which is a waste product of our metabolism, forms carbonic acid, and that associates into hydrogen ions and bicarbonate ions. This one is a very important equation because this is how you keep your blood pH in homeostasis. Now, the blood pH is very, very narrowly regulated and can only fluctuate between 7.35 to 7.45. If you have any more fluctuation, you are dead. You will not survive that. So it's a very narrow range, and you need to keep that in balance. So what are you going to do? You can't afford having fluctuations in this blood pH. So are you going to die if you drink some lemon juice? Probably not. Why? Because we have something that will buffer, that will moderate the incoming hydrogen ions. And so you can use this equation, and please note that the arrows go back and forth. They are not just one way. You can move this equation back and forth. And if you have too many hydrogen ions, then what you're going to do is you're going to breathe out more CO2. And people tend to hyperventilate when they have too much acid, to breathe out the CO2, because it will essentially breathe out like an acid. And if you don't have enough, then you hypoventilate. You keep some CO2 in to increase the amount of carbonic acid and hydrogen ions. Anytime your blood pH would go below 7.35, we call that an acidosis. And you may have heard of that as a medical term, that sometimes it happens to diabetics. If they go into, if they really don't have any insulin available, they go into a ketoacidosis. And that can be potentially life-threatening because it shifts your blood pH. And people in ketoacidosis, they will hyperventilate to try to get rid of some of this extra acid. Alkalosis is defined as a pH of more than 7.45, so above 7.45. And alkalosis, well, you don't have enough hydrogen ions, so you would compensate for that either with your kidneys, or you can hypoventilate to keep some of the CO2 in. Anyway, that concludes our discussion of the general chemistry. I'm going to stop it here and just make another recording for the organic molecules.